Okay, in this video I'm going to talk about the Vandermonde identity about binomial coefficients. So basically the identity is that the sum of binomial the products the sum of the products of the binomial coefficients, so mi and j, the sum for all such I and j such that their sum is fixed to a certain number k. So this is equal to the binomial coefficient m plus n k. So this is this holds like for any m and k. So m and k are some fixed parameters, and I and j are the indices in the sum. So okay, so let's prove this. So unsurprisingly, the proof involves the expansion of certain sums using the binomial coefficient. So let's consider the expression 1 plus x to the power m multiplied by 1 plus x, or it's better actually to write not 1 plus x but x plus 1, but I mean it's the same thing, but just for convenience it's better. X plus 1 to the power n, and this is of course equal to x plus 1 to the power m plus n, right? So now we are going to expand all three of these expressions, so all this, and this, using the binomial expansion. So this is equal, the right hand side is equal to the sum so binomial coefficient m plus n k, the sum for k from 0 to m plus n, and here we have x to the power k multiplied by 1 to the power m plus n minus k, right? So now 1 to the power m plus n minus k, so this just always 1. We can just forget about this. I'm going to remove it completely. So what remains is only this. So now on the left hand side, so we write both of these expressions. So this would be sum for I from 0 to m, binomial coefficient mi x to the power I multiplied by 1 to the power m minus I, right? But again, 1 to the power anything is still 1, so this we can just forget about this. And finally this expression is equal to the sum and j, we introduce a variable j from 0 to n, x to the power j multiplied by 1 to the power n minus j, and again this is just always 1. So okay, so the product of these two sums on the left hand side is equal to this single sum on the right hand side. So to take the product on the left hand side, these are basically the product of two polynomials. So like we have two polynomials, like let's say like alpha 0 plus alpha 1 x plus alpha 2 x squared plus and so on, and like beta 0 plus beta 1 x plus beta 2 x squared plus and so on. And so to expand this product, we simply find the coefficient before any x to the power. So when we expand this, like this would be a sum, and the term for x to the power k would be the sum would be the sum of alpha okay, let's write this more carefully. So would be the sum of alpha I beta j x. So okay, let's write this. Alpha I x x to the power I multiplied by beta j x to the power j, right? So this is, so like all of this is the sum for I and j, right? So but then, so if you want to get the term if you want to get the term in front of x to the power k, we need to sum here we need to get the sum for I. So this is for k from 0 to something, right? And inside, so the coefficient in front of x to the power k would be the sum for such I and j such that their sum is equal to k, alpha I beta j, right? So when I and j sum together give us k, then the sum of all such products alpha I and beta j would be the coefficient for x to the power k, right? So this is just normally how two polynomials are multiplied. So so this is kind of like in general case. So in our case specifically, so here, or this is kind of the equality, right? So okay, let's remove this. So on the left hand side we have basically the sum for k from 0 to m plus n x to the power k, and the coefficient in front of x to the power k is exactly the sum of this coefficient. So the sum for I plus j, this coefficient, this is alpha k, like in the notation that I gave for the general polynomials, and this is beta j, so alpha I, and this is beta j. So so m I and n j. Alpha I plus j is equal to k. So, and comparing this expression on the right hand side and this expression on the left hand side, so because these are two equal polynomials, so they must have the same coefficients for all powers of x, right? So for any k, therefore we have the sum, like this internal sum, mi and j, the sum for all such I and j such that their sum I plus j is equal to k. This sum is equal to this coefficient that we have in the sum on the right hand side, m plus n k. Yeah, and this is exactly the identity that we need. This is exactly this identity. Yeah, so this concludes the proof.